Hello there, welcome back to this channel. Today we are doing part 3 of project number 1, which is multi-way variant chips. And the task or the agenda is given the elementary gates and 16-bit variant chips that we have already done in the previous parts. We are supposed to build the following chips: OR 8-way, MUX 4-way 16, MUX 8-way 16, DMUX 4-way, and DMUX 8-way. Let's get started with the first chip, which is the OR 8-way. So we take the input, which is of 8 bits, and their addressing is as follows. So you take the first 2 bits, perform OR operation, call the output as OR 01. Take the next 2 bits and perform OR operation, and we can use the OR chip that we have done in part 1 and keep doing this to all the bits. And once you have done one layer of OR operation, you take the outputs and perform OR operation again and again until you are left with only one bit. So the input is of 8 bits and the output is of 1 bit. This is OR 8-way. So basically this is used to check if the output generated by an ALU is all zeros. So this operation will give you 1. The output will be 1 if at least one of the input bits is 1. If all of the input bits are 0, the output will be 0. So this is used to check if all the output bits, all the bits are 0. You'll see the use case later when we build our arithmetic logic unit. So you can see you're using OR operation and the input is 8 bits. So this is called an OR 8-way chip. Moving ahead with the next chip, the MUX 4-way 16. The name might seem a little bit daunting, but it's not. Okay, let's get moving. The logic. You have 4 inputs and each input is 16-bit wide or 16-bit bus. And the output, the logic is to build a chip such a way that you select only one of the 4 inputs. So just like we did with MUX 16, where we had to select between A and B, which were 16 bits wide, here we are supposed to choose out of 4. So how do we do that? This is the symbolic representation. And you have 2 selector lines or selector signals represented by cell 0 and cell 1. Let's look at the implementation. The truth table is as follows. When selector 0 and selector 1 is 0, you get A, and so on and so forth. So selector 1 will act as a higher level segregation. So if you do only selector 1, you'll get either A or B. And selector 1 is 1, gives you C and D. So for a more finer refinement, you can use selector 0. Let's look at the implementation now. So we start with MUX 16 that we have already built before. So we pass A and B using selector 1 to get selection between A and B. And similarly, we pass C and D to get this and use one more MUX chip to get the output. So notice the first refinement, the first selection is done using selector 1 and the next one is done using selector 0. All right, let's move. Yeah, so you got 4 inputs A, B, C, D. Each of them is 16 bits. So 4 inputs, each input is 16 bit and you're using MUX to select one of them. So 4, 16 and MUX gives you MUX 4-way 16. We'll look at the HDL implementation in some time. Now let's move ahead with the next chip, which is MUX 8-way 16. The problem is very similar. You have 8 inputs and 1 output. You're supposed to select out of the 8 inputs. Each input of 8 inputs is 16 bits. So this is the symbolic representation. And you have 3 selector signals. So the number of selector signals required is log base 2 of the total number of signals. So let's say you have 2 inputs, you need log 2 of 2, which is one selector signal. So for 4 you'll need 2 selectors, for 8 you'll need 3 selectors. And let's say you have 16, then you'll need 4, and so on and so forth. Let's look at the truth table. So you have 3 selector signals, and you'll be using you can use mux 4-way 16 to sort out between ABCD and EFGH, and then use selector 2 to refine further. Let's look at the implementation. So you take 4 inputs, pass it through a mux 4-way 16, which we have built before. So the project builds on layers. Once you have built a layer, it is abstracted and you use that in the next layer. So we have built mux 4-way 16 before, and we are utilizing that now. So you pass ABCD and you'll be able to select through these inputs based on selector 1 and selector 0 lines. Similarly, do that with CDEF. Same muxway 416, and in the end you'll be supposed to choose between only two 16 bits. So what do we use? Mux 16, and then you're using selector 2 to refine that. Again, 8 inputs, each is 16-bit wide, and we are using mux to select out of all these inputs. So 8, 16 and mux gives you mux 8-way 16. These were the mux chips. Now we'll start moving towards demux chips. You have demux 4-way. Notice how there's no number after way. There's no 16, right? So it means the inputs are all 1 bit wide or 1 bit. So you have input and you have 4 output pins. So you are supposed to split your input into 4 pins. So you use a demux chip. Demux is nothing but the symbolic representation is the mux chip rotated 180 degrees. And again, you have 4 output pins. So you'll need 2 selector lines, namely selector 0 and selector 1. The truth table is as follows. So when selector 1 and selector 0 are both 0, you pass the input to pin A and rest of the pins receive no signal, or it is simply 0. And when selector 1 is 0 and selector 0 is 1, the input is redirected to B and the rest of the pins receive 0, and so on. Let's look at the implementation now. Input and outputs. So we start with a simple demux chip that we have built in the elementary gates. So we use selector 1 to split the input between AB and CD. And you use one more demux to split AB into A and B, and one more demux to split CD into C and D. So 3 demux chip to build the demux 4-way. So you got 1 input and 4 outputs. All of them are 1 bit. This is the symbolic representation. So you got 1 input, 4 outputs, where each input is 1 bit and outputs are also 1 bit. And you're using demux to split the input. So demux and 4 gives you demux 4-way. Let's move on with the next chip, which is demux 8-way. Same problem, input being split into 8 outputs. all are 1 bit wide or 1 bit inputs, 1 bit values. And you have 8 outputs, which means you need 3 selector lines. Let's get going with you have the truth table, which is similar to what we have seen. The input is redirected to one of the pins, while rest of the pins receive no signal, or it is simply set to 0. Moving ahead with the implementation, we start with a simple demux step to split between ABCD and EFGH. So you have 4 inputs. You have one input that is supposed to split into 4. So what do we use? We use a demux 4-way. So ABCD is split into A, B, C, and D, and EFGH is split into E, F, G, and H. So you need one demux chip and 2 demux 4-way chips to implement a demux 8-way. Alright. You have the symbolic representation. 1 input, 8 outputs. Each input is 1 bit and output is also 1 bit. And you're using demux to split. So you have demux 8-way. 16 is not supposed to be there. It is demux 8-way. So this was the end of theoretical implementation. Now let's get going ahead with the HDL implementation. All right. Welcome back to the HDL implementation. We'll start with project number 1, multi-way variants or 8-way. So let's get started. So we pass the first 2 inputs, in 1 and in 0 and in 1, and call it as or 0 1. So we go 2 and 3, call this 2 3 4 5 4 5 6 7 6 7. Now we pass the intermediary pins as outputs as inputs here. Or 0 1 or 2 3. There is or 0 1 2 3. We pass or 4 or 6 7. Yep. Last. Connect the final to the output pin. Run this. And there you have it. Simulation is successful. Let's move to the next step, which is mux 4-way 16. So as we saw, we need 3 mux chips. Just call mux 16. Input A is A and B is B. Selector MSB would be 0. Yeah. Output, let me just call it as AB. B is D. Selector 0. And output will be CD. One more mux chip. Pass intermediary outputs as inputs here. Selector 1 and plug the output back. No syntax errors. Let's run this. Yeah, simulation was successful. Moving ahead with demux 8-way 16. Right. Okay. We'll need mux 4-way 16. In the end, you need mux 16. You pass A, B, C, and D. And you need two selector lines. Let me just choose 0 through 1. Set 0 through 1. Okay. I'll just call this A, B, C, D, E, F, G, and H. I'm not sure about the convention nand2tetris uses here. The MSB, is it 0 or is it 2? Let me run this and check. Yeah. Okay. They're going, the MSB is 2. So they're starting the indexing from the right side onwards. Yeah. Makes sense. All right. Moving ahead with the 3 mux 4-way. Okay. So we have seen we need 3 demux steps to implement this. The first one is used to split between AB and CD. Just call input 1 if I'm not wrong. Input is A and AB, CD. Pass AB here, CD here. Cell 0, A and B. Cell 0 goes C and D. Not sure about the selector lines. Let me check here. So cell 0, cell 1. Cell 0, cell 1. Yeah, looks about right. Come with us. Yeah, that looks right. Okay, let's move to the next step. Demux 8-way. So we have seen we need one demux step and 2 demux 4-ways. So 1 demux, 2 demux 4-way. So first, pass the input. Selector is selector of 2. So you got selector 1, selector 0, 1 and 2. So you use 2 to split between ABCD and EFGH. So ABCD, EFGH, CD, and then you use selector 0 and 1 to split between ABCD and EFGH. So selector 0 through 1. Just paste this here. And ABCD gets split into A, B, C, and D. Pass EFGH, E, F, G, and H. Run it. There's no error in the HDL code. Let's see if the simulation is successful. Yeah, and there you have it. The simulation is successful. We have successfully completed project 1. The next project will be building adder chips, incrementers, half adder, full adder, etc. And project 3 onwards, we'll have sequential logic where we'll be implementing memory, RAM chips, program counter, etc. Stay tuned. Thank you for watching.